Welcome to The Explainer. Today, we're diving into a massive shift happening right now in artificial intelligence. We all know and love the highly useful chatbots that write our emails and help us code. But how do we get AI to safely predict, plan, and actually act in the physical world? Today, we are breaking down the precise architecture and operating logic required for true, real-world intelligence.
Here's our roadmap for this explainer. We'll look at moving beyond language competence, the missing converter problem, JEPA and predictive architecture, and how to plan within constraints. Then, we'll ground it all in real-world system competence, and finally, look at how we govern this entire intelligence stack. Let's get right into it.
Section 1. Beyond language competence and the limit of text.
So, we need to establish a hard boundary for current AI. Large language models are phenomenal. We use them for coding, conversation, analyzing documents, you name it. But here's the catch. Language is discrete, it's symbolic, it's already highly compressed by our own human cognition. The physical world, on the other hand, it's continuous, it's noisy, dynamic, and governed by strict causal relationships. Look at these two loops. Up top, we have the language loop. Context, next token prediction, text output. Simple enough, right? But real-world intelligence needs that bottom loop. State, representation, prediction, planning, action, consequence, and feedback. Predicting a discrete token is just fundamentally different from managing physical uncertainty and actually learning from the real-world consequences of your actions.
And that brings us to the core thesis of real-world action. This isn't just theory, and it's definitely not just brand competition between tech giants. It's about the energy structure of intelligence itself, and why it's absolutely crucial for safety. The energetic paradigm, or EP, argues that intelligence demands a tightly closed loop between perception, abstraction, and constraint. We're talking about a complete operating logic here, one that includes capability diagnosis, cost-function design, and failure memory. This ensures safety isn't just bolted on as an afterthought, but is built directly into the control mechanism itself.
Section 2. The missing converter problem. From perception to fragile action.
Okay, you've probably seen those viral videos of robots doing backflips in curated demos. Super cool, right? But in the real world, they remain incredibly fragile. Why is that? Well, they rely way too much on imitation. The energetic paradigm calls this the missing converter problem. Sure, the system has sensory input, it can see, and it has action output, it can move, but it completely lacks a disciplined converter to reliably transform that perception into controlled behavior based on consequences. Without that converter, the system is just mimicking prior demonstrations. Throw a new friction level or a weirdly shaped object at it, and boom, it fails, because it doesn't actually understand how the physical world works.
This really exposes the weakness of language-only intelligence. The issue isn't that it can't say useful things, it's that it lacks a stable action-consequence engine. Intelligence only becomes reliable when prediction, planning, cost, constraint, and feedback form a closed control loop.
So, let's break down the predictive energy architecture that actually provides this loop. A world model gives a system the power to predict the consequences of its own actions. But here's the kicker. It doesn't try to predict every single pixel or molecule. That would waste an insane amount of energy. Instead, it uses this specific setup: a source for perception and memory, a converter to abstract that into a usable state, a gradient for the objective, a path to evaluate candidate actions, barriers for safety constraints, and finally, feedback and storage for failure memory. It focuses all its energy only on the variables that actually matter for planning.
Section 3. JEPA and predictive architecture and controlled compression.
How do we actually build that vital converter layer we were just talking about? Enter Yann LeCun's JEPA, the Joint Embedding Predictive Architecture. This contrast is absolutely vital. Instead of forcing an AI model to painstakingly reconstruct raw input, like predicting every single pixel in a video frame, JEPA trains the model to predict abstract representations. It's doing controlled compression. It filters out all the irrelevant variation and preserves only the stable, causal structures. The energetic paradigm takes this brilliantly simple foundation from LeCun and extends it into a complete operating logic, proving that filtering out irrelevant noise is exactly how you drastically lower the cost of planning in the real world.
But think about this for a second. What happens when those representations collapse? It's a fascinating structural failure. If the system finds a lazy shortcut and just maps totally different inputs to the exact same trivial representation, then all of its predictions become utterly meaningless. Basically, the converter just stops converting. The fix here relies on some vital anti-collapse safeguards, things like regularization, contrastive learning, and distillation. Now, in the energetic paradigm, these aren't just minor technical weeds to get lost in. They are structural safeguards. They are exactly what keeps the representation learning honest, ensuring the converter actually stays active and preserves those meaningful causal structures.
Section 4. Planning within constraints, the engine of intelligence.
Planning is where this architecture visibly breaks away from just being a chatbot. It shifts the entire control structure. Instead of just generating text that sounds like reasoning, the system actually holds a goal, simulates alternatives, and compares costs. Just look at this branching planning loop. A true world model system doesn't just guess the next step. It represents the current state at the right abstraction level, generates candidate action paths, predicts consequences under uncertainty, and, crucially, applies cost and hard constraint gates to reject dangerous paths before it ever makes a physical move.
And because safety and intelligence actually share the exact same architecture, EP insists on these 6 control layers being deeply embedded right inside the planning machinery itself, not just pasted on at the end as a filter. If a system can't predict consequences, it can't be deeply safe. If it can't respect constraints, it can't be deeply intelligent. You need representation control, so you aren't modeling fake proxies, objective control so you don't reward hidden damage, and authority control so the system knows exactly when human approval is genuinely required.
Section 5. Real-world system competence, spanning robotics, driving, and medicine.
Let's ground all this theory in the real world. In robotics and autonomous driving, imitation learning just straight up runs out of energy. A system trained purely on imitation is constantly asking what was done before. It just stores past trajectories. But a world model? It uses stored generative structure, like momentum and geometry, to ask what will likely happen if I do this right now. Honestly, this is exactly why a human teenager can learn to drive so fast. It might terrify their parents, sure, but they bring a massive, pre-existing world model of physics and space into the driver's seat.
We see the exact same thing in medicine or industrial control. Being able to summarize a medical textbook, that's merely text competence. System competence is actually predicting how a patient's physiology will change. Control competence is dynamically, safely choosing an intervention. And governance competence is knowing when to stop, when to escalate to a human doctor, and how to audit the decision later. Remember, a factory or a patient is not a text document. They are living, changing physical systems with irreversible costs.
Section 6. Governing the intelligence stack, covering open platforms and paradigm lock-in. Finally, we have to talk about scaling this up into governance. As AI starts mediating our physical reality, we face a massive sovereignty problem. Who actually controls the model? Openness without governance just isn't going to cut it. Sure, open systems diffuse risk, but they also lower the barrier for misuse. So the energetic paradigm provides this governance map. It asks the hard questions. Where exactly does local data reside? What model updates are actually moving? Who verifies the quality of those updates? This is how we ensure distributed capabilities still maintain real, traceable institutional accountability.
If we ignore this structural view, we risk massive industry lock-in, what EP calls synchronized gradient capture. You can see the broken pipeline right here. This happens when the whole ecosystem abandons the slower, much harder research of physically grounded world models, just to chase the quick spectacle of the newest chatbot demo. That kind of product pressure completely breaks the translation layer between deep research and real-world deployment, and we end up losing out on true paradigm-shifting capability.
And that leads us to the complete EPIT intelligence stack. Look, JEPA is absolutely incredible. It enables predictive representations. But the energetic paradigm is what governs this entire robust pipeline. From the language interface all the way down through perception, the world model, the cost and constraint evaluator, the action controller, and finally resting on a strict foundation of failure memory and human governance. It beautifully maps how energy moves from information to action, where it gets lost, and how we control it.
To leave you with a final thought on how all these layers connect to build stable intelligence, a language model describes the world. A world model predicts the world. But a governed, controlled system acts in the world. As these architectures evolve to finally predict and act in our physical reality, the most important question we have to ask ourselves is, who is ultimately holding the steering wheel? Thanks so much for joining me on this explainer. See you next time.